The harmonic oscillator eigenstates provide a tangible illustration of how the quantum postulates relate to a physical system. As we've noted, the harmonic oscillator is a model for vibration in molecules. So let's see how the various aspects of the harmonic oscillator solutions might play out when we talk about the quantum postulates. First of all, I want to note that in all of these, I'm going to be using the value that we found when we did this scaling to simplify the Hamiltonian of alpha is equal to the square root of mu omega over h bar. So when we look at postulate 1, which is about the quantum wave function, it basically says the quantum wave function contains all information about the system. Now we found for the harmonic oscillator that these wave functions could be written as follows, with a normalization factor that I won't go into detail on, times a Hermitian polynomial of order n times x alpha, okay, alpha being the scaling parameter for x, e to the minus alpha squared x squared over 2. All right, so this would be the form of these quantum wave functions for the harmonic oscillator. We can also create wave functions that are basically linear combinations of these eigenstates, and in fact this is a great way to generate, if you will, almost any function can be written in this way because the harmonic oscillator eigenstates form a complete set. That's a fancy mathematical way of saying that they span all of space, and they do so in a unique way because they are orthogonal to one another. All right, so with postulate 2, we start talking about the operators of quantum mechanics, and that they must be linear operators. Well, we've seen that the Hamiltonian operator for the harmonic oscillator really looks very similar in form to the Hamiltonian we've seen for things like, for example, the particle in a box. It's just the second derivative with respect to the coordinate x. We do have an additional term, though, which is due to the potential, written this way. Now we've seen that we could take this version of the Hamiltonian, and by using our scaled coordinates, in other words this parameter alpha, we can actually rewrite this Hamiltonian in a scaled form that makes it look like this: minus 1 over 2 d squared dq squared plus q squared over 2. All right, so this is a way of also writing that Hamiltonian, and both of these Hamiltonians are Hermitian operators, so they're going to have real values for their eigenvalues, and their eigenfunctions are all going to be orthogonal to one another. Now, when we get to postulate 3, we're talking about measurement of energy, and in particular, if we make a single measurement of the energy using the Hamiltonian operator on some arbitrary state, so maybe I should write that as phi, we're ultimately going to have to get one of the energy levels of the system. So if the system is a harmonic oscillator, that means that we will always measure h bar omega times n plus a half, which means that in this case, we've picked out the part of phi that was equal to the nth eigenfunction for the harmonic oscillator. Postulate 4, I should have numbered these postulates as I gave them. Postulate 4 tells us if we make a series of measurements of something like the energy, that we're going to basically measure something that is an average value. So for example, the measurement of energy done several times might be given by an expression that looks something like this, when dx psi star of x with the Hamiltonian psi of x. All right, so this would be one measurement. We also could measure the average value of the position, and that would be given by an integral that would look something like this, with x as the operator in the middle, and I forgot the dx over here. All right, so these are two manifestations of this where these psi's now could be either an eigenfunction of the harmonic oscillator or a linear combination of eigenfunctions of the harmonic oscillator. So either way, these things would hold, and these would provide us a means of calculating average values. Finally, postulate 5 tells us how the time dependence of the harmonic oscillator might be governed. It would be governed using the time-dependent Schrodinger equation, which we can write this way. And this big psi of x and t again could be written as a linear combination of the eigenstates of the Hamiltonian, and the Hamiltonian itself would be operating on it with this result. So if we were to study the time dependence of a harmonic oscillator, this would be our operational equation for doing so. Now, I want to go back to this statement that I wrote up here about the average position of a particle that is a harmonic oscillator. And if I were to write this out, and let's do this carefully down here, okay, I would be writing this, for example, for an eigenstate of the Hamiltonian, of the harmonic oscillator. It would look something like this. Okay, but what do these eigenstates look like? Well, remember that they are, since this is not changing that state at all, this would be essentially equal to x times this eigenstate quantity squared dx. But these eigenstates have components that are written up here at the top that we can easily square. So for example, this eigenfunction would be equal to the normalization constant squared times a Hermite polynomial squared, and then the Gaussian function squared would just give us e to the minus alpha squared x squared. All right, now this is an even function. That is to say, if we plug in minus x for x, we'll get the same thing back. This is just a constant. So what happens with these Hermite polynomials? Well, I'll remind you that the Hermite polynomial for 1 was equal to 1. For 0 is equal to 1. For 1, it's equal to 2x. For 2, it's equal to 4x squared minus 2. And you can see that if I square each of these, if I square the first one, that's just 1. If I square the second one, that's 4x squared. If I square this one, I'll get 16x to the 4th minus 16x squared plus 4. Notice that what's happened is that in each case I get only even powers of x when I square these things. That's going to generally be true whether or not this is an even value for the Hermite polynomial or an odd value for the Hermite polynomial. So in other words, this whole function has to be an even function. The process of calculating the average position, however, though, is going to take an even function times an odd function. So when I integrate from negative infinity to infinity, I will always get the result that the average position is equal to 0. All right, so this is really building in, if you will, the symmetry of the harmonic oscillator, that we're always going to get 0 for that average position, and it reflects also the symmetry of that problem. Now let's look at the eigenfunctions for the harmonic oscillator. I've drawn here the first few eigenfunctions on a map of the potential surface, and I've labeled those eigenfunctions by their quantum numbers, 0, 1, 2, and 3. And there's some observations that I would like to make about these eigenfunctions. All right, first of all, the number of nodes that we see in each of these eigenfunctions is simply equal to the number n. Okay, n equals 0 has no nodes. N equals 1 has a single node. N equals 2 has 2 nodes here and here. N equals 3 has 3 nodes here, here, and here. And we would find that this is similarly true. We also know that when I increase the quantum number n, I get an energy that is greater than its predecessor, which basically is telling us that the more nodes that are present in the wave function, the higher the energy level. Now this isn't uniquely true, but it is true for one-dimensional systems, that as you put more nodes in the wave function, you will always get a higher energy level. When you have more than one dimension, that's when you can have some cases where you could have a lot of nodes in a dimension that doesn't add a lot of energy, and therefore have more nodes than having an energy where you'd have a single node in the higher energy dimension. I didn't say that very well, but I hope you can get the meaning there. Okay, so in general, we're going to be increasing quantum numbers. We're going to get to increasing energies, and when we have a single dimension like one-dimensional system, then more nodes is going to translate to higher energy. You'll note that when n is equal to 0, 2, or 4, we end up with having an even function for our eigenfunction. So look at this function down here, the Gaussian. Even function is one that's going to be symmetric about this line. Okay, so this is symmetric. It looks the same when you go both ways. This function here is symmetric. It looks the same when you look both ways. When n is equal to 1, 3, 5, and so forth, then we end up with an odd function. Okay, which basically means we switch sign. So when we cross this barrier here, we switch sign. This part of the function is upside down relative to this part of the function. Similarly, for the n equals 1 eigenstate, this part is upside down relative to this part. So we always have odd functions when n is odd. All right, now all of these functions, all of the functions psi of n, extend to infinity. That is to say, they have non-zero values as x goes to plus or minus infinity. They asymptotically approach 0 as they go to infinity, but they never quite get there. All right, this again is a feature that is true of many quantum mechanical systems, especially those that do not have an infinite potential. We saw that in the case of the particle in a box, those functions did go to 0 at the edges of the box, but that was only because the potential was infinite there. All right, so finally, I'll note here that the symmetry of the potential is what guarantees that the eigenfunctions of this potential will either be even or odd. So this is telling us that there is an implicit and intrinsic relationship between the symmetry of the potential and the quality of the eigenfunctions that we get from that potential. And this shouldn't be surprising because those eigenfunctions arise from the potential. The kinetic energy operator is an even function, if you will. It's the second derivative. So the eigenstates themselves must reflect the potential in some sense. So a symmetric potential is going to give us something that will either have even symmetry or odd symmetry as we go higher in a quantum number.